So you have to confirm. So let's pretend I start from here. So we discussed last time we discussed the empty universes with the characteristic of the scale factor to be linearly increasing as a function of time. And let's assume the universe is, the energy density of the universe that we are thinking of is very small compared with critical density, so that this empty universe is a fairly good description of this particular universe that we are considering. And we also think about a light source or galaxy at redshift value z. And we observe this galaxy at today, T0, this is today, in our convention. So if I write, we have a relationship between the redshift and the scale factor. That's basically this. I have a t divided by a time of emission in the denominator, and in the numerator, I have a scale factor at the observation. But since we are observing it today, scale factor by definition should be unit. So I'm going to have 1 over scale factor evaluated at time of emission. But for this universe, I have a scale factor is t over t0. So it's t0 over t emission. So let's rewrite in terms of TE, so that's easy. Time of emission is time of today divided by 1 plus z. One thing in this case, T0 was overtime. Overtime is the inverse of Hubble parameter as of today. So we can rewrite this also H0 inverse divided by 1 plus z. Now we are asking, now I brought this small chair so that I can sit. I'm getting older. We are asking how far is this galaxy? One way of answering this question is to calculate the proper distance. So we discussed this proper distance right now. So T0 is the integral. So we have scale factor evaluated today and integral. Let's say from the distance is nothing but r, because this is 1. This is what we already discussed in the previous chapter. Also, we discussed null geodesic. What I mean by null geodesic is the distance that the light traveled. So that's basically, now I have a speed of light. I think you can still see it. Integral 1 over a and I integrate over time. And in this case, integral range is from time of emission to when we observe, which is today. And we discussed also in chapter 4, this has to be equal to basically this. So now we can say this should be equal to that. So what do I mean by that? I can express proper distance of a light source as of today at the distance of redshift z can be this. So I have c integral 1 over a dt t equal to 0. A is here, the inverse of A is this. So I have C T0. I'll be. And T goes to the denominator at the bottom. So 1 over integral of 1 over x is log x. So I have log T0 over TE. Don't say that you don't know this step. Log x dx integral is, I'm sorry, -1 should be log x. If you don't know this, I think you have to drop this class. All right, so if universe is static, then CT0 should be the distance, speed of light, times the time of travel. But you have a log factor. And we can rewrite this. So T0 over TE is 1 plus C. So it's CT0 log 1 plus C inverse. T0 over T is 1 plus C, so there's no inverse. Or this is T0 is inverse of O. So it's CH0 log 1 plus Z. Should be the relationship. So let's take a look at, I'm going to share the screen. And let's take a look at this figure. So in horizontal axis, I move this term to the left so that I have H0 over C dP T0 is my vertical scale, and horizontal scale is redshift Z. So for now, let's take a look at the red one. So this dashed one. And one thing to note is that now the vertical scale is expressed in what I call log scale, as opposed to linear scale. And I don't know whether you have seen this stuff or not, but when I say log scale, the scale increases instead of linearly. It's scaling power of 10. So here we are looking at from 0.0001 to 0.001, 0.1, 1, and 10, and 100, something like that. And also horizontal axis, which is Z, is also log scale. It's actually exponentially increasing, but why is it called log scale? I think the reason is that if you take a log, then what you get is a linear scale. So that's the actual plot. So I am going to repeat. So Z is here, and this guy is on the y-axis. And for empty universe, we have something like this. Notice that this value is around 10 to the minus 2. And the maximum value that I'm plotting is not exactly, but 10 to the 2. So let's take a look at the definition of Z here. So for today, A is equal to 1. So to satisfy this, Z has to be 0. So when we say redshift is 0, that's today. And back in the past, scale factor is a small number. Normally, if we assume on expanding universe, the universe must be smaller back in the past. So this thing on the right-hand side, this number will be a big number, and it's bigger for the more previous time. So if Z is greater than 1, that's test only universe. If Z is bigger, that is only a universe we are talking about. So if you approach to this, you're approaching to today, but this is log scale, so you never reach to 0. So this is today. If you go that way, it's past. So qualitatively, what it tells us is that if the galaxy that you are seeing is the one that's very close to you, then of course the horizon distance is also short because it's near to us. But if you are looking at an object a bit away from you today, then the horizontal distance is also big. Remember, this is log scale. But the thing is, if you move further away, then the increase of the horizontal distance is being saturated. Why is that? That's because the scale factor. And this calculation is telling us This is essentially coming from this. You know, if you don't have this term, horizontal, I'm sorry, horizontal distance we'll discuss later. What did I say? Proper distance. Proper distance is only a function of t. So here, when t0 is te is similar to d0, this is you could expand this and so on. And the leading order is constant, so it's linear part here. But because of this term, this saturation occurs. Now, one more thing. From this, if we want to calculate proper distance, not today, but the time of the light emission, for that particular galaxy, you are saying that the distance as of today must be reduced by A at TE. ATE is essentially 1 plus Z inverse. So this is saying that this result, C over H0 log 1 plus Z, and you have to divide by 1 plus Z. Therefore, if we are talking about the proper distance, not today, but at the time of emission of the galaxy at a Z for almost empty, practically empty universe, then this would be the expression for such a distance. Let me show you the picture again. So this picture, second picture in the figure 5.3 appeared in your lecture note. This is the behavior. So you can't see me. So let's take a look at only the red ones here. So these guys, so similar to proper distance today, but as you move on, it actually decreases. And the decrease of proper distance at the time of emission is now because of this term. And this term is again essentially from the scale factor. So really far away object that was actually closer to us because back in that time, universe was shrink enough to be having this sort of, I shouldn't draw this because it's a different vertical scale, but this behavior is from essentially this, and fall off has to do with the expansion, non-expansion of universe by that time. All right, I hope that's clear. Now that's all we want to say about empty universe. Now we move the subject to a single component universe. So let's do that. I only have, this one is a little wet because I cleaned it up before the class. We will see a wet blackboard. So not blackboard, it doesn't look black to me. It looks to me dark green. I don't know why people call it blackboard. Maybe in old days, the color of the board was really black. I don't know. I should have done this one day before. So that this is dry. I hope that's not too bad. All right, so single 5.3. 5.3 single component universe universes. Why is plural? Because we will talk about matter only universe, radiation only universe, or dark energy only universe, and so on later. But we first want to discuss in a very somewhat general way. Let me remind you, that's the Friedman equation for multi-component universe. We had 8 pi g over c square and vector 3, and we need to sum over all these different components, epsilon I 0 and a minus 1 plus 3 equation of state parameter. And there's a curvature term. No, since I have, this is the term that we have to have. So this was the generic Friedman equation of multi-component universe that we discussed in last class, I think. But now we assume only one component, whatever that is. And let's consider now flat universe. T-I-A-L-L-Y. Flat. That means our kappa is 0. So things will be easier to deal with. What that means is I have a dot square. I have only one component, so there's no summation. Three c square. And let's say epsilon 0 only, because I only have one component. And then a minus 1 plus 3 omega, and I also drop the index I from there because I only have one component to play with. So let's take a look at this. So this is first order. Because I only have a dot, but it's a square, non-linear. differential equation to solve. And the obtaining the solution for this single component universe is your homework. And I am going to give you a little hint. Hint is, you assume the solution is proportional to time power of something, let's say P. Then plug this back into the differential equation and find out what P should be to satisfy this equation. And the answer is, and this is your homework. I don't want to touch this. And the power is a little funny. I have 3 plus 3 omega, W. Did I say omega before? It looks omega, so let's call it omega. And the second thing to note is that this T0, oh, one more thing. This is a differential equation, so in order to solve this, you need a boundary condition. This is a first order, so you only need one boundary condition. And that is, what is the boundary condition that you have? Anyone knows? You hate questions. The only boundary condition that you have is T0, scale factor at T0 is always unity. So that's the boundary condition that you have. All right, so using that boundary condition, you can also get the T0. And that's your second homework to be done. That's 1 over 1 plus omega, or W, density equation of state parameter, C square 6 pi G epsilon 0 1/2 should be the answer. So don't confuse this epsilon 0 with this permittivity in vacuum that's appearing in electromagnetism. This is the energy density of a single component universe that we are dealing with now. In fact, we are not going to, at least for this chapter, we are not going to discuss electromagnetic interaction at all. So that shouldn't be anything to do with the electromagnetism. Okay. So this is your solution that I didn't prove, and this is your T0 that you have to work on. Now, I want to know Hubble constant or Hubble expansion rate as of today. So whenever we set up a model universe, we want to know what should be T0, what should be Hubble constant, what should be proper distance as of today, and proper distance at the time of emission of a photon that is arriving to us today, etc., etc. So by definition, this is A dot at T divided by scale factor at T evaluated at T is equal to T0. So I think we could get it from here, or even from the solution. But let's get it from there. Let's try. I don't know what I did. I forgot. But since I have a dot, so a dot is equal to, I'm gonna take square root. So that's a pi g over 3c square at epsilon 0. I'm gonna have a minus 1 plus 3 omega divided by 2 because I'm taking a square root. And I have a, then I'm gonna have minus 1. It doesn't really matter because we will be evaluating t is equal to t0. So regardless of this value, a is set to be 1. So that's my h0. That is equal to epsilon 0 over c, 8 pi g over 3, 1/2 d, my h0. I want to express my h0 in terms of t0 minus 1. I am now slightly confused. Is this right? Okay. So I take square root, so I get this. I have to square root this as well. So there's a square root going on. I want to express h0 with t0. So for that, I want to do epsilon 0 over c, 8 pi g over 3, 1/2. And I multiply t0 and t0 inverse so that this equation is valid. So but t0 is here, which is 1 over 1 plus omega and c square 6 pi g epsilon 0 1/2 times t0 inverse. The reason that I do this stupid thing is because now things will be canceling out. C, epsilon 0, G, pi, all canceled out. Except some numerical factor. I have, this becomes 4, this becomes 3. So numerical values that you are going to get is, and these are the square root, so that can go out. So 4 becomes 2, 9 becomes 3, 1 plus w. Keep saying omega or w back and forth to confuse you. And then t0. And the reason is we want to express t0 as the now 3, 1 plus omega over 2 Hubble constant inverse as well. Something, oh no. The t0, this goes where there and h0 was there, so there's no flip. It's not flip. 3, 1 plus W/2 should be D. In the case of empty universe, T0 was inverse of Hubble constant. I think, no? Yes. But for the universe with something in, but that universe is flat, spatially flat, then I have this extra factor. But it's a constant. It's decided, that constant is decided by which kind of energy density that we have. All right. What we can also say is if omega, I'm saying omega, if W is greater than -1/3, then this is greater than 1, so that my T0 is smaller than Hubble time. Therefore, T0 is less than H0 minus 1. What does it mean? In this case, the age of the universe is younger than Hubble time. Or if you use the other inequality, if W is less than -1/3, then my universe will be older than Hubble time. So that's on impact of this equation. Yeah, we are seeing the limitation of short blackboard. I don't want to erase some part of this, but no space. So let's at least, I don't want to erase it now. So let's do the following chain of flipping it. I had lunch, but I feel hungry now. Okay. The next topic is if we express our energy density in terms of the scale factor, it was something like this behavior. So for that, if we want to express the energy density as a function of time for a single component universe, we have E0 and A was, I remind you, this was T over T0 2/3 plus 3 omega, I think. Yeah. So you put this back in there. So you will have for t first, I have this times that. So that is cancelled with this, except I have -2. I have t0 times minus simply t over t0 minus 2. Yeah. Now it's funny because the reason is now Et is independent of omega. So the energy density at any given time is independent of what you have in your single component universe. That sounds strange a little bit, at least to me. Why is that? One way of, well, one reason that I can say is our scale factor has dependency on equational state parameter. Also, our energy density, when we express in terms of the scale factor, that also contains dependency on the equational state parameter. But when we express the energy density in terms of time, that dependency was cancelled in such a way that if you express energy density as a function of time, now the result is that it's no longer dependent. It's independent of the density of state parameter omega, or it doesn't matter. It's independent of what you have in your universe. I was going to say it doesn't matter what matter you have in your universe, but it's not easy to understand. So I was trying to avoid the word matter because otherwise you will be confused. So that's another observation that we have. Now, we are talking about spatially flat critical density as of today is equal to 0. If you are not sure about what I'm talking about, you should go back to chapter 3 or 4 or so. So this is only true. It's not generally true. This is only true for a flat universe. So let's use this notation for only this discussion. And for T0 was which one? I don't remember which is what. T0 was where is it? I am T0 was 2 over 3 plus 3 omega H0 minus 1. I'm wondering if that's what I did. Fine. Now I'm confused because what am I doing in the previous? Okay, I was completely lost because I was hungry, I think. I said T goes there, H0 goes there. So it doesn't flip. And I flip. So it's, and you are not complaining. You are not paying attention. What's going on? Wow, you're sleeping. All right. People make a mistake. And I am also a human being. So forgive me. But don't make a mistake in your exam. You'll get penalty. All right, so this is your correct expression. So what are we going to do? So we want to use this. First of all, let's take a look at the epsilon 0. Which was equal to the critical density. And I remind you that I didn't write it here. So the critical density appeared in where? That does anyone know? You're not responding, which is a usual response from my students. So I'm not surprised, but okay. Critical density, we define in chapter 4, 3 critical, normally, we C square, A pi G Hubble constant square. That was the definition. And for us, we want to calculate this epsilon 0 appearing in our single component universe. And that happened to be equal to the critical density. So we have this vector, 3c squared, 8 pi g. And we have this h0 square. So I'm going to have 4, 9, 1 plus w square, and t0 minus 2. Okay. So let's say 3, 2, that gives me 6. I have c squared over 6 pi g 1 plus w square t0 minus 2. It's the expression for epsilon 0 or energy density as of today. Or you can equivalently say critical energy density for such a universe as of today. And we want to now calculate the energy density of such a universe at any time. That's given from there. So that's epsilon 0 times this times T over T0 minus 2. So that gives me T minus 2. So I want to separate 1 over 6 pi 1 plus omega square, and I have C square over G and T minus 2. Now we have to remember what we did in chapter 1. This guy, we can re-express this guy, c squared, speed of light squared, divided by gravitational constant. We want to express that in terms of the Planck unit. And it will turn out to be, this is going to be E Planck scale and L Planck scale minus 3 time Planck minus 1. I'm sorry, square. So that's square. Plus, yeah, C plus. That's the third homework that you have to work on. So let's use this. So I end up with my energy density that's the expression. So when things are very small or at the Planck scale of time, I remind you that the time of the Planck scale, that was on the order of 5 times 10 to the minus 44 seconds after the Big Bang. So that's extremely small number, small time, perhaps the smallest time or oldest time that you consider. Is essentially, so this term is cancelled because I'm evaluating this at t is equal to Tp. Let's forget about this because it's just order 1. So that's the Planck energy scale divided by the volume of the Planck scale volume. And that has to make sense. So conclusion so far is, for spatially flat universe with single component, if we go back to the Planck time, then the energy density scale should be something that we expect. Planck energy divided by the Planck volume. One more thing is, that does not mean this is realized in our nature or not. What I am telling you so far is, this framework of a Friedmann equation is telling this, but it's not necessary that that is realized in nature. This is only a theory that describes the gravitational effect as of today. We have many experiments and observations that's consistent with general theory of relativity, but that's only today. You know, we are talking about black holes and gravitational wave detection these days. Black hole merges and they radiate gravitational wave, and people are detecting them. It has been a hot topic in recent years. But that's all the what we call classical general theory of relativity. If you go to this, you somehow have to put quantum mechanics in. We don't have such a, well, we have some models, but we don't have correct theory. So if you are challenged, you can work on things like this. All right, so that's that. I want to do one more thing. So again, we do the same thing. We want to calculate proper distance. So we are looking at on light source at the redshift z. Again, just like what we did it for empty universe. I want to have 1 plus z. That's the ratio of J, which is 1 by Y ratio at the time of emission of the photon, which is reaching us at today. The answer is right there. T, this is 1. So this would be nothing but, let's say, T E over T0 and minus 2 over 3 plus 3W, and minus because AT is in the denominator. Or you can flip these two, and that's in fact what I did in my lecture note, which is the same thing. Now I want to get an expression in terms of TE. So what I have to do is 1 plus Z, and I make a power of inverse of this. So that's minus 3 plus 3 omega over 2. So I have minus 3 1 plus omega over 2. Then I get rid of this guy, and then I multiply T0. And then the next step is I want to use this to get rid of T0 so that T0 is appearing here. So this factor has to come as is. So I have factor 2, 3, 1 plus W. I'm going to have AC0 inverse. I have H0 inverse. So that I have in the denominator. And now I have this term. And now I want to be consistent with the textbook. So I want to have this 1 plus z term in the denominator. That gives me 1 plus z, and I get rid of negative sign, 1 plus w over 2 as an exponent. Why we are doing this? Well, we want to do the following thing. We want to do proper distance as of today. So that's speed of light, dt over a, from time of emission to today. So that's C, and inverse of scale factor as a function of time is this. So I have t over t0 power of 2 over 3 plus 3w dt. So this thing will come out and it will be 1 over whatever that is, plus 1. And I have speed, don't forget the speed of light. And let's take out T0 power of minus 2 over 3 plus 3 omega. That's the constant. And I have T 2, 3 plus 3w plus 1. That should be evaluated from TE to T0. It's just a boring calculation. I want to erase this part. So I have 3 plus 3 omega plus 2. Am I doing right? Yeah, I think something's wrong. So there should be, I just erase it. Damn. Yeah, that's right. Why am I? Okay. So it's in the denominator. So we have to have negative sign. So that's negative here. Now things should make sense. So I have this plus gives me 3 plus 3w, but I have minus 2. So that gives me 1 plus 3w in the bottom. So I have C and when you evaluate this from T0, then this will be becoming T0. And you have same, it's not easy to see. I'll just give you an answer. you take out T0 and you have a extra factor. That's the factor that I'm talking about, W, essentially from this guy. And the numerator, I have 1 plus 3W, which is from the numerator of the denominator. And I have, you take out T0, 1 minus the ratio of T emission over T0, power of 1 plus 3 omega divided by 3 plus 3 omega should be the answer. And if you don't believe me, you can work on this integral. You know, sit down, have a deep breath, and then work on this. And that will give you an answer. This is only true when omega is not -1/3. Otherwise, this blows up. That's one thing you want to know. Another format, instead of T0, I can have shouldn't be thinking about empty universe. We have T0 was 2 over 3 plus 3W H0 minus 1. And if we want to get rid of T0, this will cancel with that. So I have C vector 2, 1 over 1 plus 3W H0, 1 minus, and TE over T0 is here, and I have 1 plus Z, so I can have this over here, and I can replace this is 1 plus Z. In terms of minus 3 plus 3 omega divided by 2. And I have to multiply with that, so that will be canceled. So I have minus 2, 1 plus 3 omega. That's my guess, and I am right. Or at least the same as my lecture note. So this is now T0. So the proper distance of a certain object at the distance of redshift Z calculated at today. Do I want to go to the picture now? Okay. Time is over. So one last thing. So this guy, now we can take a look at other curve from radiation to matter and universe with lambda. So that those are the single component universes. And again, I'm applying normalized dp of today as a function of the redshift. So what you want to remember perhaps is that for the radiation, the increase of proper distance is smallest, and the second one is the matter. And when you have nothing, it increases faster than 2 cases. And when you have dark energy or cosmological constant, then your horizontal distance is the largest, or it's moving, increasing fastest as a function of redshift z. Okay, I am late by 3 minutes. Sorry for that, but let's stop here. Do we have any question? You know, today or next week, the mathematics that we have to deal with is heavier than normal ones. So things are, actually it's not complicated, but for some of you, maybe it's complicated. So don't be fooled by mathematics. What we want to pay attention to is the implication of the equations that we deal with. So if you have questions, you can ask me now, or if you are shy, you can send me email, or you could drop your question on KakaoTalk. So, okay, let's stop here, and then I'll see you next week. Have a nice weekend. Bye-bye. Now I want to mark. I want to stop recording. Stop.